Yes, please.
Just a question, do you used to see the videos from these lectures?
Yes, I saw the videos when I have question or something like
Yes,
that.
teacher.
Okay, thank you. Glad to know
Yes,
that.
no problem.
Okay, that's really good to know. Okay, I'm recording now. So we have replaced, in this case, the upper limit, which is infinite, with that variable. So this integral is a proper one instead of an improper integral. So we can solve this integral as usual with whatever method is needed. And then once we have the solution for this proper integral, we take the limit for the result when n reach infinite. And then we'll get the solution for the improper integral. And once we do that, we will have the solution for the Laplace transform operation. Okay, just remember we need to solve this integral in order to have that transform. So why are we doing this? Why we will want to have a new function called the transform? Well, because we can take a differential equation into an algebraic one. That's why. And we know how to solve many types of algebraic equations. So we're going to dip into the knowledge of how to take Laplace transforms in several ways. So this is the first one. This is the finding of a Laplace transform using the definition. If we have a function like this one, we want to solve this improper integral, then first of all, we replace the infinite with a variable, and then we proceed as usual. So in order to find the integral of e to the ct is quite simple. We can use substitution and we can define a new variables as ct, and then we find the differential view, which will be cdt in this case. So dt can be replaced by du divided by t, by c. What do I see? So we use factor 1 over c, and then we have like the integral, which in this case is e to the ct, and we evaluate that using these limits. We evaluate in n and 0 and do the subtraction, and then we have something like this. From here, we can take the limit whenever n, and here is n, tends to infinite. And from here, we can see that the limit will be -1 over c. If you remember your classes from differential calculus and you remember the application of limits, we can determine that the limit would, when n reach infinite, in this case, is equal to -1 over c. The n is over here, so e to the cn reach zero, as n reach infinite. Remember the graph of an exponential? In general, we have something like this. So whenever n reach infinite, this term will be zero. Of course, if that graph is valid if and only if c is a negative one, because otherwise we'll have something like this. The exponential will have a graph like this one, and then as n reach infinite, e to the ct will be infinite too, so there will be no limit. So the condition in order to have a limit for this function is that c is less than zero or negative. That's the only way to have a limit. So we provide that condition or that restriction, c being negative, then we have a limit, and that limit will be -1 over c. And remember, c is a -1 or a negative value. Okay, that's a general process in order to find the solution for an improper integral. So in this case, we have found the integral of e to the ct from 0 to infinite, and that result is -1 over c. As always, c is negative. So once we have reviewed how to solve improper integrals, we can find the Laplace transform of a very simple function. Let's say that f of t is equal to 1. So the Laplace transform of f of t will be simply the Laplace transform of 1. And then we can apply our definition for Laplace transform. And yeah, there's not really a whole lot to do here. We just replace the number 1 instead of f of t, and then we are left with this integral, e to the negative st times f of t, which is 1. And we have already done this. We have solved the integral from 0 to infinite of e to the ct. And we found the solution to be -1 over c. In this case, c is equal to -s. So c is negative, that's the restriction, so we can use the result as a valid one. So the result will be simply 1 over s. We just replace c over here with -s, and negative times negative give us a positive sign. So we can say that the Laplace transform of 1 is equal to 1 over s. And we can see that if we try to find the integral of 2, we will have a number 2 over here, which goes out of the integral, and we are left with 2 over s, and so on. So the Laplace transform of any number will just be, or any constant will just be n over s. Okay, and that's our first result. So whenever we have a constant, we already know that the Laplace transform of that constant is just the constant divided by s. And it will make sense this for later, because we don't need to find the integral whenever we are dealing with a constant. And this result will be valid if S is positive, is S is greater than 0. So we always, just remember, we always have some kind of restrictions. In this case, we say C should be negative, but that restriction can be changed to S being positive. Why? We have already done that, I think. No. We have this solution over here, -1 divided by -S, but this will be valid if and only if -S is less than 0, right? Because that was the restriction for C. The restriction was this one. So as soon as -S is less than 0, then this will be valid. And this restriction can be changed to this one. If we multiply both sides by -1, then we need to change the operator over here. So this will change to S greater than 0. Okay, what about if f of t is equal to e to the at? And we want to find the Laplace transform of f of t. Okay, we need to replace e to the at in our definition. And our definition says we need to multiply e to the negative st times f of t, and here is f of t. Now we need to find the value for this improper integral. Let's do that. So the product of these two exponential is just simply this one.
Teacher, this is the way that we use to resolve or to solve phasores. I don't know how to say it in English.
Phasor.
Phasors?
Yeah, from electricity, right?
Exactly.
Yeah, you can use Laplace transform to solve, to find the solution of a circuit whenever the power supply is an alternating current. AC can be done using Laplace.
Oh.
Why? Because you need to transfer a function of time to a function of frequency. Whenever you are doing AC analysis, maybe you are interested in doing analysis in terms of frequency instead of time. And that's why you use Laplace transform. Okay, yeah, that's one of the applications. So this product will be this one, e to the a minus s times t. And then in this case, we can use the previous result where we have e to the c. So in this case, c will be equal to a minus s, and we already know the solution, and that will be -1 over c. And we can take this sign into account. So we multiply it by a and negative s, and we are left with this result. And the restriction will be that this has to be negative, otherwise it should be greater than a. That will be the restriction. So remember, in order to write down the Laplace transform of a given function, there will be some restriction applied to it. In this case, S should be greater than A. So we have a positive number in the denominator. So please remember this result. Remember that the Laplace transform of e to the at is equal to 1 over s minus a. Okay, so if we have something like e to the 3t, the Laplace transform will be simply 1 over s minus 3. The Laplace transform of e to the omega t will be 1 over s minus omega. The Laplace transform of a negative number, e to the negative 5t, will be 1 over s plus 5. This is an s, this is a 5. So I ask you to remember this result. So we have a constant. We know that the result will be that constant divided by s. If we have e to the nt, the Laplace transform will be 1 over s minus n. Okay, and why I'm asking you to remember these results? Because this will let us work through these formulas instead of solving integrals. That's quite a lot simpler to remember a formula than to solving an improper integral, right? So we have two important formulas that we can use instead of solving improper integrals. Let's work with one last example using the definition for the Laplace transform. Let's find the Laplace transform of sine of at. So we replace in our definition f of t with sine of at, and then we try to find the solution for this one. Okay, first we turn our improper integral into a proper one. We just change the infinite limit with the variable, and then we'll take the limit for that variable reaching infinite. So now we can solve this integral as usual, and we can use maybe integration by parts, the integration by parts method. And if we do that, we'll get something like this. Using integration by parts, we'll have this integral again. So we need to apply integration by parts once again. And you know that in the next result, we'll get this integral again. And then we do the usual trick, moving this term to the left side, because in the left side we have this integral, and then we just divide all of the right side by 2 and we are done, right? That's a classical integral. And here is the result. As I told you, in the second integral, we'll get this integral again, and then we can move it to the left after doing some simplifying process. And finally, we'll get a result like this one. The Laplace transform of sine of at will be equal to a divided by s squared plus a squared, provide this a positive number or a positive expression. So I will let you to review the solution, but this is the result. The Laplace transform of sine of at will be a divided by s squared plus a squared. And we can do something similar to find the Laplace transform for cosine of at, and that will be equal to s divided by s squared plus a squared. Now, whenever you need to take the Laplace transform of a sine or a cosine, you already know the solution. We already know the Laplace transform. And from here, we can see, we can do something very practical. We can take these results into a table, and then we have a table called the transforms table. And then we'll use the table instead of solving integral results. And that's the way we're going to work with Laplace transform. As you can read over here, usually we just use table of transform when actually doing the computing of Laplace transform. So we don't used to use their definition in order to find the transforms for given functions. So before doing some examples using a table, let's review this fact. Is we have two functions of time, let's call those functions f of t and g of t, and we have any constants a and b, and we want to find the Laplace transform of this expression, our function f of t times the constant a, plus our function g of t times the constant b. The Laplace transform will